In the previous class, we discussed the case of a particle trapped inside a potential well with infinite barrier. Since the barrier potential was infinite, the particle was trapped completely inside the well and there was no probability for finding it outside the well. Real potential wells are not having infinite barriers. Instead, they have a finite potential barrier. So let's see what happens to the case of a particle trapped inside a potential well with finite barrier. Consider a particle of mass m moving inside a potential well defined by this potential. It has a potential V0 for x is equal to less than minus a in this region and x is equal to greater than plus a, and we assume that the potential is 0 inside this well which has a width of 2a. So here we can consider three regions, region 1, 2 and 3. In region 2 the potential is 0 and hence the time independent Schrodinger equation for the particle inside the well can be written d square psi by dx square plus 2m e by h cross square psi of x is equal to 0. Solution to this equation will be exactly similar to the case of infinite barrier potential with symmetric and antisymmetric wave functions. In region 1 and 3, Schrodinger equation becomes of the form d square psi by dx square plus 2m by h cross square into e minus v0 in psi is equal to 0. Now let's consider the case the energy of the particle is less than the barrier potential, that is E is less than V0. Then this equation can be written as d square psi by dx square minus 2m by h cross square into V0 minus E into psi of x is equal to 0. So we have made this rearrangement to ensure that this quantity is a positive quantity. 2m by h cross square V0 minus E is a positive quantity, and then since we are changing the sign here, we put a negative sign in this position. Now if you take 2m by h cross square into V0 minus E as some positive constant alpha square, this equation can be simplified as d square psi by dx square minus alpha square psi is equal to 0. And the general solution to this second order differential equation is psi of x is equal to c e raised to alpha x plus d e raised to minus alpha x, where c and d are the constants to be determined. In region 1, you know that x actually extends from minus a to minus infinity, minus a to minus infinity. So as x approaches minus infinity, we can see that the first term in this expression becomes finite, but the second term diverges. Hence, for wave function to be finite, as the limit goes to minus infinity, the constant d has to be 0. Therefore, we can write psi 1 equal to c e raised to alpha x for this region, or in the region 1. In region 3, x goes from plus a to plus infinity, and hence the wave functions become finite only if this constant c equal to 0. So we can write in region 3 the wave function as psi 3 equal to d e raised to minus alpha x for this entire region. In region 2, we had d square psi by dx square plus 2m e by h cross square psi is equal to 0, and for which we will have a solution a sin kx plus b cos kx if we take 2m e by h cross square as some constant k square. So we have seen in the previous class that the wave function in region 2 can be either symmetric or antisymmetric about the origin. Let's initially consider a symmetric wave function in region 2. That means the constant A equal to 0 in the solution of psi 2. We know that the wave functions must be continuous at the boundaries between the regions 1 and 2 and also between 2 and 3. So that means at x is equal to minus a and at x is equal to plus a, we have these conditions. At x is equal to minus a, psi 1 and psi 2 must be same, and at x is equal to plus a, psi 2 and psi 3 must be same. So this continuity condition leads to this equation psi 1 c raised to minus alpha a equal to same as psi 2 b cos ka at x is equal to minus a. Similarly, this second boundary condition, or the boundary condition at the second boundary, leads to this equation d e raised to minus alpha a equal to b cos ka. And the continuity of the first derivative at the boundary gives us another equation c alpha e raised to minus alpha a equal to bk sin ka. And the continuity of the derivatives of the second boundary gives us one more equation minus d alpha e raised to minus alpha a equal to minus bk sin ka. Now if you subtract equation 5 from 4, we will get c equal to d, and if you divide equation 7 by 5, we will get alpha a equal to ka tan ka. So let's keep these things there, and let's see what is the case in the next condition, where we assume antisymmetric wave function in region 2. So in this case, we assume that the constant b is equal to 0 in the expression for psi 2. Now again, we know that the wave functions must be continuous at the boundary, and the continuity of the wave function at the first boundary gives us this expression c raised to minus alpha a equal to minus a sin ka, and this continuity demands d raised to minus alpha a is equal to a sin ka. And we have two more continuity equations, that is from the derivatives at these two boundaries. So the continuity of the derivative of wave function at this point, or at the boundary of region 1 and 2, gives us c alpha e raised to minus alpha a equal to ak cos ka, and a similar continuity at this boundary, in the boundary between 2 and 3, demands this equation minus d alpha e raised to minus alpha a equal to ak cos ka. And here if we add these two equations, equation 10 and 11, it shows us that c is equal to minus d, and if you divide equation 13 by 11, we get minus alpha a is equal to ka cot ka. These equations 9 and 15 can be solved numerically or graphically to obtain the energy eigenvalues. So let's define alpha a equal to gamma and ka equal to beta, some other constants. Then these two equations become beta tan beta equal to gamma and beta cot beta equal to minus gamma. Then if we add beta square plus gamma square, this will be 2m v0 a square by h cross square. And this equation represents a circle in the beta gamma plane with a radius square root of 2m v0 a square by h cross square. To get the solution, let's plot beta tan beta and beta cot beta against beta, along with circles of radii square root of 2m v0 a square by h cross square for different values of v0 a square. Now this is how it looks like if you plot the functions beta tan beta and beta cot beta in the beta gamma plane. Now let's draw circles of radii square root of 2m v0 a square by h cross square for different values of v0 a square. And you can see that these circles intercepts the other curves at certain points. As beta and gamma can have only positive values, the intersection of these circles with beta tan beta curve in the first quadrant gives the energy levels for n is equal to odd integers like 1, 3, 5, etc. And the similar intersections with the curve beta chord beta gives the energy levels for n is equal to 2, 4, 6, etc. For a given particle, the number of bound states depends the height and width of the potential barrier through the factor V0 a square. If the radius is greater than 0 and less than pi by 2, then we have only one intersection. And if the radius is greater than pi by 2 and less than pi, then we have two intersections. And if the radius is greater than pi but less than 3 pi by 2, then we have three intersections like that. Thus, there will be one energy level for the first symmetric wave function for V0 a square greater than 0 and less than pi square h rho square by 8m, and two energy levels, uh, one for the symmetric and one for the symmetric and one for the antisymmetric for the function V0 a square greater than this quantity and less than 4 pi square h rho square by 8m, and so on. There will be three energy values for the next one and four energy values for the next one, and so on. The first three bound state eigenfunctions, if you plot, it looks like this. The wave function in region 2 is similar to those in a potential well with infinite wall that we analyzed in the previous class. However, they have tails in regions 1 and 3. The points at x is equal to plus a or minus a are the classical turning points for the well. Wave functions have tails beyond these classical turning points. That is, there is a finite probability for the particle to be found outside the well in the immediate vicinity of the boundary. In other words, quantum mechanical particle can tunnel or leak into the classically forbidden region. For the plots n is equal to 1 and 3, we have symmetric case, and we have seen that the constant C is equal to D, and hence the amplitudes in region 1 and 3 are of same sign and behavior. For n is equal to 2 case, we have seen that the constant C is equal to minus D, and hence the amplitudes in region 1 and 3 are of opposite behavior. You can see it here. In regions 1 and 3, the wave functions exponentially approach 0 from the boundary as given by equations 1 and 2. Now, if the energy of the particle is greater than the barrier height, then alpha in this expression becomes imaginary, and hence this equation will leads to an oscillatory solution in region 1 and 3. So that means the probability density is distributed over all space and the particle is not at all bound.